Okay, so you are on. Please go on.
Okay, good. Okay, very good. Thank you for the opportunity to talk. I'm sorry I could not be there in person. I, in fact, just got back from Melbourne a couple of days ago, and things are busy here. Go ahead to the next slide, please. So when we talk about exploration, the idea that most people have is that of putting your foot in a place where no one has ever been before. Okay, next slide. But just in the last 60 years, that's 60 years out of the entire history of this planetary system, we've begun to see the emergence of what we would refer to as intelligent machines. And these are now doing more exploration in terms of planetary work off Earth than humans are at the moment. And so this is kind of the backdrop. I want to just kind of tell you my personal journey down this and where there are benefits from one versus benefits from the other. Next slide. So those of you who may know me, I've been designing underwater equipment for over 4 decades. And we started with the what might be considered the golden age of open circuit exploration in caves. And all of that was pushed to what might be considered ludicrous limits when you consider how many tanks have to be carried. Next slide. And following up on that, I started designing rebreather systems as early as 1984. This is a dual Mark V system that was used at Wakulla Springs in 1999. Next slide. We were also using redundant propulsion systems also back in 1999. Go ahead, next slide. We were using habitats. This was actually a mini saturation system where we recovered the divers from 30 meters underwater depth and then took them to the surface for the final 14 hours of decompression. Most of the dives were on the order of 24 hours. Next slide. There's a quick recap of just the in-water portion of the dive. It was roughly 5 hours was the typical bottom time at 95 meters depth. Next slide. But the why in the road, if you will, the fork, for me came on that project in 1999. It was sponsored by National Geographic and Rolex, and that allowed us to build a machine to build 3D maps of flooded caves. And so the idea was to build a 3D map of Wakulla Springs in Florida. Next slide. And the person on the right there is Jill Heinerth, who is well known in technical diving circles. And as you can see, we mounted this device on the front of one of our propulsion vehicles, and then the diver would drive it through the tunnel. And it had a high-grade inertial guidance system on board and a 32-point array of sonars that would fill in the cross-section of the tunnel as the vehicle was flown. Next slide. And so here is a 3D model in a point cloud form. These could be reduced to meshed fly-throughs and things like that. I'll show you some later. The different colors represented different missions. So there were 28 actual dives that were done during that project, and each one collected information. A total of 32 kilometers of tunnel were mapped on that project. Go ahead. But the thing that happened on that that to me was important is there was a meeting held at the end of the project. It was a 3-month project with 165 people involved, and the divers who were the lead divers provided critiques of the engineering system, so the rebreathers, the propulsion vehicles, the mapper, and finally at the end, one of the programmers who was involved with the mapper stood up and he said, if we'd had another $1 million and another year, we would not have needed any of you divers. And that, of course, got a lot of attention. But just 2 years later, NASA put out an announcement looking for ideas for how to explore sub-ice oceans on Europa, Enceladus, and Titan. And we were fortunate enough to obtain a $6 million grant from NASA to begin looking into that. Next slide. So the result of that was a vehicle called DEPT-X. It's an acronym standing for Deep Phreatic Thermal Explorer. It had a rated depth of 1 kilometer, and we explored. Next slide, please. Well, so just to mention here, Carlos had a very interesting discussion previously there. What we did, and this was in 2002 and 3 and 4, we developed a real-time version of 3D SLAM, which is a simultaneous localization and mapping concept based on roughly 64 different discrete sensors shining around the vehicle. Next slide. And so what the world looks like to the vehicle is a series of faceted hits from sonars, and then the red beams you see are valid sonar hits, and there's a mechanism for getting rid of reflections and aliases and things like that, so that you eventually build what amounts to a true map of the world around you. Next slide. So we took that to Cenote Zacuton, which is perhaps as well known as the Hranice Abyss. It had been attempted to be explored by Sheck Exley and Jim Bowden in 1994. And as many people know, Sheck died on that dive. I knew Sheck very well, and so it was somewhat kind of in his honor that we went back with a robot and explored Zacuton. Next slide. This is looking out. It's 140 meters in diameter. It has a 16-meter overhung roof, and then below that is the extent of the pit, which goes down to over 335 meters. Next slide. This should be a video. See if you can go ahead and play that, please. Okay, so what you're seeing here, the red dots are the validated sonar hits. The yellow beams are the attempts to acquire data. Some of those are rejected. A lot of them are retained. And you begin to see that as you move down, this is a test case called Cenote La Pilita. It's about 105 meters deep. And the yellow line, if you can see that in the middle, is the trajectory of the vehicle as it goes down. And we have obstacle avoidance code on the vehicle. So if it gets within 10 meters of anywhere, it will retreat back up to the top. Very simple code for its day. Okay, next slide. Go ahead and skip it again. There we go. So here is this is a projected map of the entire complex at Zacuton. Zacuton is on the left. It's 335 meters deep. There's Caracol, Verde, and La Pilita, that little test case we showed you there. They're all hypogenic caves formed by sulfur-based acidic water. Next slide. So NASA was more interested, however, in under ice operations. And so we spent a half a year in Antarctica on 2 separate missions in 2008, 9, and 10. This is Lake Bonny in the dry valleys. Next slide. We bored a 5-meter hole through the ice, and then the vehicle went down and built a 3D model of the lake, as well as the 3D chemistry that was in there, with the idea of searching for extremophile life forms. Next slide. This is a 3D model live. We were actually watching this form while the mission was underway, of the head of Taylor Glacier, which is the ice body that forms Lake Bonny. And underneath that, at a depth of about 30 meters, we were able to discover a hypersaline solution that led to the discovery of some novel microbes that were associated with that area. Next slide. So the real ice, when you talk about under ice exploration, are the big ice shelves in Antarctica, and the Ross Ice Shelf is in fact the largest. It is the size of France, and what is underneath that is completely unknown. Next slide. So we got a NASA grant. This is a movie. Go ahead and play that. I hope maybe you have some sound with that. It'll kind of give you an idea. This was August in 2015. So that's a video, by the way. I don't know if you can play that. Yeah, there you go. It gives you an idea. So we were hitting roughly 100 km/h gusts out there, and the temperature was minus 75 Celsius. So rather a hostile place to be doing robotics. Yeah, that's where we were working. So next slide. So this is a long-range version of an under ice vehicle. It's called Artemis. And I have a short video here, which will kind of give you a feel for what it was working in. So if you could go ahead and show the movie on the next slide. So we build our robots from scratch, both the structure, the mechanisms, the propulsion, the electronics, everything that goes in there, we build at our lab. This is a 1.5 metric ton vehicle. Has a range of 20 kilometers. And so this was right before we shipped it to Antarctica. That is Mount Erebus in the background. We're about 25 kilometers from McMurdo Station. And we drilled a 20-meter deep hole through the head of the Ross Ice Shelf and set up a laboratory there. The vehicle was boxed up, flown in on a C-17, and then taken out to the site on tracked vehicles. And you'll notice it's a horizontal vehicle, and yet we have a vertical hole to go through. So the thing that's unusual about this is the vehicle is designed as a 6 degree of freedom machine. It is both neutrally buoyant vertically as well as neutrally rotationally buoyant. So we can operate it in any attitude. So we're going to drop it down vertical. Once it stabilizes, it will flip itself over and then go off on its mission. So down the hole it goes. And there we are. It goes through a maneuver to get rid of trapped air. And then it takes off on a typical 10 to 20 kilometer range mission. This is the underside of the ice cap. This is all crystalline frazzle ice. Get an idea here, we're building multi-beam maps under the front of the Ross Ice Shelf. Much like Carlos, we have a mission control center that keeps track of what's going on. And finally, from a distance of about 400 meters out on any given mission, it detects this oscillating bar of light. It has a LED array in it. The machine vision cameras on the front of the vehicle track that in. It will autonomously lock itself in, tell us that it's ready to go home, and up it goes. So you can stop the video there and go to the next slide. Okay, so usually we're building prototype vehicles, and nobody was sure how the vehicle was going to behave and whether it might get in trouble. So we built a rescue vehicle called Sunfish, another 6 degree of freedom machine with a less range, roughly 8 kilometers. And we had a grappling system on the front of it that we installed in Antarctica in case we had to rescue the vehicle. Next slide. So this is a little video, if you could play this, please. This will give you an idea of the degrees of freedom of control this vehicle has. So it's important that we have this kind of maneuverability for a couple of reasons. One is that if you're going to go through a labyrinthine cave on your own, you need to be able to maneuver vertically and horizontally. And the other thing is that the sensors only point in one direction. Like Carlos was saying, we're using a multi-beam system for the main 3D imager here. And because that only has a 120 degree field of view, you have to do a little dance underwater to complete a complete spherical scan. Next slide. So we are in Peacock Springs, Florida here. And this is what we see as divers. Next slide. This is what the robot sees. So it's mainly operating off a point cloud, and then it has a very good awareness of where it is. Yeah, okay. You can go to the next slide. So like Carlos, we typically have a mission control center, but the important thing here is that Sunfish is completely autonomous. We have a data link for observing how it is operating, but on board there are about 400,000 lines of software that implement behavior-based exploration. And I'll give you an idea what that is. This is not a choreographed response. It actually reacts to the environment and then makes decisions on where it is based on a series of very high-level goals. Next slide. Okay, this is a movie there. Okay, it's auto-playing. This gives you an idea. This is a replay of the data space that is recorded by the vehicle. So you can see it's scanning. Once it's done scanning, it does a series of calculations, and you notice these white spaces, volume. That is a set of possible vectors to continue exploration, and it will follow the one that allows it to do the largest amount of new exploration in any given move. If it sees a side tunnel that is smaller, it remembers that, and it will take the bigger one trying to go in a direction we give it. We're going to try to get 1 kilometer north. It will attempt to do that, but if it ends, it will come back, check out the side tunnel. Here's the same data in a mesh version. This is the traverse from Peacock 1 to Portugal in northern Florida for those cave divers who are familiar with that. It's a very popular training site. And these pendants that you see on the roof, those are real. Those are not stalactites. They are solutioned out in the caves. Some of them provide rather restricted spaces, so the robot slows down when it's through that. Next slide. So these were kind of backgrounds to what we were trying to do. And we wanted to take it to a place where we could really test it in completely unexplored territory. And so we took it to Namibia. This is Dragon's Breath Cave there in the slide. It's the world's largest subterranean lake. And I have a little video. Go ahead for the next slide. This will give you an idea of this operation. And hopefully you can turn the sound up so you can hear the narration.
In northern Namibia, there are a couple of very deep caves that happen to be water-filled, and divers have explored these caves to significant depth, but they're running into the limit of human physiology, the depth that they can dive. And also the passages are so huge that even when they're down there, even though the water's crystal clear, they can't see the walls. These places are unmeasurable by humans. The goals of the Dragon's Breath expedition are to take a small underwater vehicle, an autonomous underwater vehicle, an AUV that we've developed at Stone Aerospace, and send it into these caves, Dragon's Breath and Haroseed Cave, and use sonar to map these places that humans can't see and dive the robot beneath depths that humans are able to explore. From the surface down to the bottom of the cave at Haroseed is about 100 meters. Almost all of that is on rope. Sunfish itself is about 100 pounds right now. It's a prototype, it's still heavy. In addition to that, we've got probably another 200 pounds of fiber, tools, rafts, stuff we need to operate down there right now.
Sunfish is at 60 meters depth, proceeding down the chimney.
Inside the vehicle are about 400,000 lines of software that control autonomous behaviors, meaning robotic behaviors that it does on its own. And so it can, for example, by itself, without us doing anything, explore into an unknown cave. And that's what we're doing here.
Here, we really want to work at depth. So the divers have told us that they've been down to about 130 meters. They've seen down to maybe 150. Part of our goal is to push beyond what they're able to do physiologically. So here, we're working with a depth limitation of 250 meters. And I'm hoping we'll go that far. And it certainly seems that the caves have the potential to do that.
207 and heading down.
Everything was going great, you know, and it's those kind of things that in the back of your mind, particularly as a cave diver, you know, you don't go too far before you kind of look over your shoulder to see what's behind you. You know, it might surprise you, you know, like it's gone to zero visibility or something, you know. So when I look at this, it's like everybody's getting excited, and we're seeing. I mean, we had just discovered a gigantic new chamber down there, and we were starting to go deeper, and we figured, all right, it's not going to be much further before we hit the structural depth limit of the vehicle, which was 250 meters. And so we were actually expecting within minutes to hit that number and say, okay, that's it. I had glanced over at the head-up display, and there's a series of numbers there that I knew what they were. And the one that I was looking at was depth. And suddenly it stopped and put up a number that said NaN, which means in computer speak, not a number. And I immediately froze, and I looked at Neil and I said, oh, geez, we may have just lost the vehicle.
State estimation is down. We have lost control of the vehicle.
You know, within 30 seconds, we had gone from this euphoria of going, all right, hey, this pit is going down. Where's it going? Let's go see, you know? And then the next one was this cold feeling coming up your spine of, we may have just lost a $750,000 vehicle. We had a depth sensor triggered a failure of the operating system.
We are seeing telemetry data now.
Luckily, they were able to reboot the vehicle. The problem then is it came up basically mindless. It didn't know where it was. It didn't know which way it was pointing. Normally, it had this map that it had built, and it would just zip right home along that map. Well, now they had to do the whole thing over again. Why is that a problem? Because the power was dropping down, and so the clock was ticking. The sand was running out of the hourglass, and these guys now, under pressure, had to explore back.
The mission control guys were able to drive the robot back out, but it was a stressful journey the entire way. The exploration of Harisib was a success on multiple fronts. This is the largest chamber we've ever mapped. It was the deepest we've ever gone. And now we feel that we're ready to go on to Dragon's Breath.
Okay, we can go to the next slide, please. I'm hoping that everybody over there was able to hear all the audio on that video. It's cracking up over here for the video feed. So you may have noticed a couple of things here. One is that there was a green small fiber connecting the computers to the vehicle. There are a number of ways in which we can operate this system. And so you saw a couple of those there. The joystick is basically in ROV mode. You can move it, you can turn it, you can send it where you want. It's a very low power reserve that we have in case something goes wrong. We have the ability to script a mission, to choreograph with back up, please. We have the ability to script the mission. And then when you get into what we would call behavior-based AI, we have something called supervised autonomy. And because water absorbs radio frequency, we can't do Wi-Fi connections or any other type of RF telemetry. So we use the fiber optic link to the vehicle. The vehicle does its own thing, but we need to be able to observe what's going on. And then the final one is you cut the fiber and the vehicle runs on its own. We have found, now you can go to the next slide. We have found that it's extremely helpful to be able to see how the vehicle is responding to unknown, unstructured environments. And we have built vehicle deployed fibers of up to 15 kilometers in length. Currently, Sunfish has dual capability. There's a standard 4 kilometer and a long range 8 kilometer fiber that can be carried by the vehicle. And it acts very much then like a cave diver with a dive reel. So you don't have to worry about the vehicle getting caught if you do this. And at some point in about the next year or so, we feel that we're ready to remove the fiber altogether for explorations. Next slide. And so where is all this going? When we started building rebreathers, the best available computation was an 8-bit processor that achieved about 3,000 floating point operations a second. It was not even enough to calculate time to surface for a decompression calculation. And so we had to have 3 of them operating in parallel to do that calculation. Well, today, on a single 23 millimeter square chip, we're achieving 7 teraflops, which is not that far from the computational capacity of the human brain. And if nothing else, what it does is it allows you to implement complicated procedures that otherwise would have been bogged down in computational cycles. We don't have to be quite as elegant as we were with an 8-bit processor. So most of our code is now written in Python and utilizing commercial modular code segments. So what we're expecting here is an acceleration towards full AI within the next 2 to 3 years. Next slide. So this is where we're headed, long range. This year, the vehicle range will go up to 25 kilometers. We have a 6K cinematography camera and a dual machine vision camera in there for tunnel inspections. In February next year, in roughly 3 months, we have the 3rd Wakulla expedition. This one will be entirely autonomous. We will have a couple of divers on standby in case they're needed or to film the vehicle. But the goal is to untethered map the first kilometer of Wakulla with full imagery of the sidewalls. And that's kind of a trick because the tunnel is 50 meters in diameter and the visibility these days can be less. Within the next year, the plan is to upgrade the depth to 1 kilometer range. And then moving on, we are doing work with Bishop Museum out in Hawaii to build what might be called a diver assistant, a vehicle that follows a team of scientific divers and then does things that they want it to do. So we're starting to see, the advent of a portable machine that can be used either as an assistant to a diver or as a independent device for exploring. And as everyone knows, there's a lot of deep diving sites out there that right now are pretty much beyond human range. When you get past 250, 280 meters, it's a dangerous proposition. And just to let you know, I haven't given up on the human side. I'm working very closely with Henry Harris and Craig Challen, looking to implement a hydrogen rebreather system for the Pierce resurgence. We'll probably follow up on that with sunfish. So that's my talk. Next slide is the last one. Then we can take questions whenever you want.